Okay, so we make so it's a pleasure to introduce Michael Dumbser, who will speak about a simple. No. It gives me more pleasure. Higher order is scheme for a chemical threshold and hyperbolic obligation of steel mechanics. This facilitates viscous conductive fluids and elastic solids.
Thank you very much, Peter, for the kind introduction. Thank you very much, Lorenzo, Giacomo, for this kind invitation. Yeah, well, I am here in one of the two capitals of Italy concerning Numerical methods. Yes, so I just have to say from top that we will use different approach, namely the ADER schemes developed originally by Millington, Tito, Vladimir Titarev, and many other people. And well, today I will just give a very, very rapid overview of our numerical schemes, and then I will discuss a very recent actually application to hyperbolic formulation that is able to describe at the same time solid mechanics and fluid mechanics. Our collaborators are Ilya Pleshkov, Eugene Rumensky, Olindo Zanov. So the starting point for our schemes is actually a formulation that fits the title of this workshop. Yes, so we have a hyperbolic balance law. It's allowed to contain non-conservative products, stiff algebraic source terms, and of course F is the classical nonlinear flux tensor. And many systems that are relevant in science and engineering can actually be cast into that form. So we will not only discuss a unified formulation of continuum mechanics, but also a unified formulation of discretizations that contain as a special case both classical DG finite element schemes as well as finite volume schemes. So the discrete solution in each cell, UH, is represented by piecewise polynomials of degree n, and then the fluxes and source terms are computed from a different discrete solution that is called WH, which is represented by piecewise polynomials of degree m, where m is larger or equal than n. And in order to compute the WH from the UH, actually we do what you would do in a classical finite volume scheme, namely we apply a reconstruction operator. For that purpose you need to define a stencil, of course, so a cell and some neighbors. And then we require just basically a weak identity between the polynomial that we are looking for and the polynomial that we know just by L2 projection. Yeah? If you look at a finite volume scheme, in that case phi the test function would be 1. So this equation would just mean you require integral conservation. Now we require integral conservation in some sense also for the higher order moments. Okay, so that gives rise to a unified class of numerical methods. At first order of accuracy, everything coincides. DG and finite volume schemes are all the same. At second order, you just have, say, second order finite volume scheme. Sorry, you can't read this. This means a P0, P1 scheme. Yeah? So you involve cell averages and you compute fluxes by piecewise linear polynomials. The classical DG scheme, P1, P1, yeah, you evolve directly piecewise linear polynomials and use them to compute fluxes, and from third order onwards you get a new intermediate class of schemes that I will not discuss further, but basically you have on the right branch DG schemes, on the left branch finite volume schemes within one unified formulation. So now concerning time discretization, well, in Trento we are a small island, is in an autonomous region in the Alps, so we do stuff our own way. So our idea is to use fully discrete schemes that don't rely on molecular stages, but that can be basically cast into a predictor-corrector form where the high order of accuracy in time is now achieved in a predictor stage. In other words, once you have a reconstruction polynomial WH in your cell, you need to evolve this polynomial somehow in time, right? Because if you check the finite volume formulation, you have time averages of the fluxes to compute if you have a fully discrete scheme. And in, say, the classical ADER schemes proposed by Tito and Vladimir Titarev, they use the Cauchy-Kowalewski procedure to convert space derivatives into time derivatives. This procedure has two disadvantages, I would say. First of all, the classical version is not able to deal with stiff source terms. Now there is an implicit version of Cauchy-Kowalewski, so that can actually account for stiff source terms. However, if you want to apply that procedure to relativistic MHD equations, it becomes quite complicated. So that is why we advocate, say, a local space-time DG predictor approach. So that means we solve a weak form of the governing PDE. Right? The Kochelewski is based on Taylor series and strong form of the PDE, whereas we solve a weak form of the PDE in space-time locally. So that means we transform the PDE into a space-time reference element, that's just for convenience. Multiplied with a piecewise space-time test function now. This theta is a space-time test function of degree m. Integrate the whole thing over a space-time control volume, like the tiles and the kitchen, right, in the graphics of Gabriela. But now we don't integrate that term by parts, because we want to keep it locally. Okay, so we only integrate this term by parts in time, because we want to introduce the initial condition of our local Cauchy problem. Okay, so we integrate only by parts in time, and what you get is basically an integral over the upper bounding surface in time, which is known, as you can extrapolate the data from within the cell, and also the integral over the lower time surface, known as your initial condition. So basically what you have done here is you have chosen a numerical flux in time direction, which means you do upwinding in time, because the causality principle, and information flows from the past to the future. Now you just insert all this space-time ansatz stuff, and you get at the end of the day something like an element local nonlinear algebraic system, which you can easily iterate with this simple fixed point iteration. In the stiff case, of course, the source term, which is hidden in there, needs to be done implicitly, of course, otherwise this can't work. Now, then once you have computed these coefficients Q hat, you have a space-time polynomial in each cell, and now you can insert this just simply in your classical scheme. So you now take the PDE again, multiply with a spatial test function of degree n. Now you can, well, either if it's a conservation or you could integrate that term by parts. If it's not a conservation, or we use this approach of path conservative schemes forwarded by Toumi, Pares, Castro, et al., where you basically have an integral over the smooth part of your solution and an integral over the boundary and over that takes into account the jumps. Okay, and your Riemann solver is basically hidden in that term. Now this integral over the source term is apparently explicit, right? Because you know already QH. You have done the implicit part locally for each cell already before. So the summary of the algorithm is you have 3 steps. You reconstruct, you evolve the data, and then you insert these space-time polynomials into your favorite scheme, say into a finite volume method or into a DG scheme. And remember, for n equals 0, you get a classical finite volume scheme. For n equals m, you have a DG finite volume scheme. So now, continuing with the topic of Gabriela. So as soon as you go to the astrophysics community, especially to the relativistic astrophysics, there is a complete mess. The PDEs are not only a lot of PDEs, but they contain stiff source terms, and you cannot even convert conservative variables to primitive variables analytically. So here, just to show how this method works in the presence of stiff source terms, this is the set of relativistic resistive MHD equations where you have this current here given by Ohm's law, and this sigma is the conductivity. If this sigma tends to infinity, actually, then this system relaxes to the ideal relativistic MHD equations. And so what we do now is we have an exact solution for ideal relativistic MHD, and we solve the full system with stiff relaxation in the stiff relaxation limit and check with the exact solution of the asymptotic limit system and check whether we get the correct order of accuracy in space and time. Actually, this is the case, apparently, so for third order schemes from finite volume on the left to DG, third order, fourth order, and up to fifth order of accuracy, both in space and time, also for the relaxed variables, which is the electric field. So, for stiff source terms, I mean, tell me if I'm wrong, but I think it's not so easy, even with Numerical schemes, to get, say, asymptotic, preserving, and high order of accuracy schemes. Now, we wanted to incorporate all that into a space-time adaptive code. Basically, we write just a simple finite volume formulation here. U bar is the cell average. These are just the numerical fluxes and the jump terms due to the non-conservative products. And what I also would like to advocate is, in the context of ADER schemes, say time-accurate local time stepping in the context of adaptive mesh refinement is trivial, thanks to the existence of the predictor. I just would like to illustrate this. So okay, our stuff is element-based AMR, so the data are organized in a tree. And here, this is now the kitchen, but with subtiles. So these are basically the elements which are big in space and which are allowed to run big time steps. These elements run the smaller time steps. And how this works now, unfortunately, we don't see the color here. Basically, if you want to compute a numerical flux across that interface, what you need is the predictor solution QH from the right and the left. So if you suppose that all elements start at the initial time t0, you do a reconstruction, each element can actually compute this predictor. QH is fully local. There's no interpolation, no communication needed. But once you have the predictor, you can compute a flux. So everything you need is there, right? But you can compute a high order accurate flux in time. Once this small element has done its update, it will write its flux also into some memory variable of the neighbor just to make sure that you are conservative. Okay, so then you proceed. If you want to ask how to do Reno reconstruction at this intermediate time, because remember these guys have not yet been evolved, but it's easy because you have the predictor which is valid here, so you can produce a virtual cell average at any intermediate time you want. You can run this fully anarchically. Each element could run really at its own time step. Here it's really organized, but you can do this on a moving mesh with full anarchy, and you get a fully by construction conservative scheme that is high order accurate. Yeah, so there are just some convergence rates. The overhead for the AMR here is acceptable, I would say, between 15 and 25% if you count the cost. There are just some nice pictures. There's a double Mach reflection problem where you can zoom into the features, but let's say nothing special for people in astrophysics. They use this AMR stuff every day. I just would like to make some publicity for the talk of Raphael tomorrow. You can couple this AMR with a posteriori subcell limiting for the DG finite method. Now, if you put all these ingredients together, here you see the soft shock 2 problem. For example, you see the adaptive mesh refinement. This has been computed with a 10th order, nominally 10th order ADER DG scheme on an originally reasonably coarse mesh, and let's say now a very simple exact solution. So it was not a, you can't see the exact solution, but it's basically on top of the numerical solution. But this will be the topic of the talk of Raphael tomorrow. So now we have, say, this machinery in place. Now we want to make use of it somehow. And very, very recently, actually last year, Peshkov and Romensky have proposed, to my knowledge for the first time, a complete unification of continuum mechanics that contains, as special cases, classical solid mechanics as well as fluid mechanics of viscous heat-conducting flows in just one single set of PDE. So that's the PDE system. Actually, it follows the framework of hyperelasticity. So that means you have mass conservation equation, momentum conservation equation, so P is a classically hyperdynamic pressure, and sigma is the viscous stress tensor. Then this is an evolution equation for basically the deformation gradient, that is what the strain in solid mechanics, that is what you need. To compute the stress tensor in solid mechanics usually, as if Hooke's law would be a linear relationship between sigma and A. You have some relaxation source terms here. This guy is called strain relaxation. Then you have another equation that looks very, very similar to the momentum equation. Actually, we call this the thermal momentum equation, where J is the thermal impulse. Okay, we will define this guy later. And temperature takes the role of pressure. From this J, you can compute the heat flux in the total energy conservation. Right? If you look at these equations, if you forget for 2 seconds about these two intermediate equations and the entropy equation, this looks like the system of compressive and Navier-Stokes equations, just that now the stress tensor is not given a priori by, say, a phenomenological rheology like for compressive and Navier-Stokes, but this sigma is directly computed from A, as I will show later. This is the entropy equation, so entropy is assured to increase, this physical entropy. So this is a so-called over-determined PDE system, because actually you see there's one equation too much, well, either the entropy equation or the energy equation is redundant. Yes? And Godunov already in the 1960s, and that is not so well known as his Riemann solver, studied these over-determined PDE systems. And actually he found that this PDE system is consistent if and only if the total energy E is actually a potential that depends on all the other state variables. So once you specify the total energy as a function of all the state variables, density, entropy, velocity, deformation gradient, and thermal impulse, then all the other non-convective fluxes, like the pressure, the viscous stress tensor, and even the dissipative source terms, are a direct consequence of this choice. So basically, you only need to specify one equation of state, which will contain everything. So basically, pressure is defined as rho squared times the partial derivative of E with respect to rho. Temperature is defined in that way, and so on. For all the other terms, yes, you always can see that the stress tensor, heat flux vector, the dissipation source terms are all related to partial derivative of the energy potential with respect to the state variables. I will talk a little bit later about these two functions, θ1 and θ2. They are positive functions of the relaxation times, τ1 and τ2. And so we will see this is actually a hyperbolic system with relaxation, that is then later able to reproduce all the effects that you want. So the choice of the energy potential, and that is very important, yes, you should remember that, is actually the simplest possible one. Okay? So there are three energies. One is, say, the microscopic energy, as you say, ideal gas equation of state, for example, or the equation of state, the thermal equation of state for a solid. This guy is the classical kinetic energy, so that's the macro scale of your flow. And this is some intermediate mesoscale. So that will basically is the energy due to this thermal impulse J and the deformation gradient A. And if you look at our choice here, that's basically the simplest thing we could do. It's just a simple quadratic function of J and G. Tf, which is the trace-free part of the matrix G, which is just AT times A. Okay, so A is the deformation gradient, say the strain. Okay, then we come with this G, which is a simple combination, and Tf is the GTF is the trace-free part. So basically, it's just a simple quadratic energy potential that we choose. That is important to remember because later we will show that the Navier-Stokes stress tensor will fall out of this choice automatically without having to impose it a priori. So now let's check. So the stress tensor is given by that relation, yes? So it's related again to the derivative of the energy potential with respect to A, and you get this explicit formula, right? So the stress tensor is a direct function of G and this deviator of G. And the strain relaxation source term also is a function of the derivative of the energy potential with respect to the state, with respect to the strain tensor A. And you get this relation here for the strain relaxation source term. Likewise for heat flux and thermal impulse. Yeah? So once you have chosen the equation of state, this stuff is a consequence. Yeah? So you have no other choices to make. Yeah? The model gives you what the heat flux vector and the strain relaxation and the thermal impulse relaxation source terms have to look like. Now that is what Godunov found is to make this overdetermined PDE system compatible. It means that, well, okay, you have a total energy conservation law and you have all the other equations including the entropy equation, and so they must be compatible in some way. So if you take all the previous PDEs, you multiply them with certain factors, you actually can show that at the end of the day they sum all to zero. And the energy conservation was just a consequence of all the above mentioned PDE. If you use now these factors, these thermodynamic dual variables, yes, and you apply the Legendre transform to the energy potential, you get a new potential, it looks like this. And then you can rewrite the whole PDE system, I only show the left-hand side here, yes, in that form. And this can be shown to be symmetric. Yes, so these matrices A and B are both symmetric. And actually, if the energy potential E is a convex function of the state variables, then A is a positive symmetric positive definite. So it's proven that it's hyperbolic right from the beginning. You don't need to do anything else. You just need to choose a convex function for the energy potential, which is what we have done. We have chosen a linear quadratic function. So that's a result. Right? You don't need to combine it. This falls out of this theory. So now what we want to show is that if you reduce this relaxation time, actually what is the meaning of the relaxation time? It means how long does an element or a material element remain in the neighborhood of the surrounding material elements. Well, for a solid, it's clear if it's elastic, yes, so that this time should be infinity, right? Because The solid is always surrounded by the same neighbors. Whereas in a gas, this thing is always changing. So in an ideal gas, tau tends to 0. So now let's check the limit. So we just write this evolution equation for the time evolution of the tensor G. We do the Cherepanenko expansion of G, and after some calculations, yes, so you set all these individual coefficients to 0, you get one important result, that the deviator of the G at the 0th order level has to be 0. But that means, if you apply the definition of the deviator, it means that the G0 has to be 1/3 the trace of G0 times the identity matrix. Okay, so if you call this guy just simply little g, you see that the tensor G actually is something like a constant times the identity matrix plus some higher order terms. You actually can compute the constant G in terms of known variables, namely the density and the reference density. So if you insert this into the stress tensor and you do some additional calculations, so you compute the evolution equation of the deviator of G and you retain the leading terms only, now, okay, if you look at this stuff, this looks already very nice because we want to go to the Navier-Stokes stress tensor, yeah, so this is good. If you now compare the right-hand sides, what you get is at the end that the stress tensor in the limit when tau tends to 0 is just this constant multiplied with, but well, what you know, compressive Navier-Stokes stress tensor. But we have never put this thing into the model explicitly. This is the consequence of the choice of a quadratic energy functional E as a function of A. Okay, whereas in Navier-Stokes, I mean, this is basically postulated from the start. Whereas here, this is a consequence. And for tau to 0, you get Navier-Stokes. For tau to infinity, you solve elasticity equations in the same PDE system. You can do the same calculations for the heat flux, and at the end you find that in the stiff limit, the heat flux relaxes to the classical Fourier law. Okay? But important to stress that it's a first-order hyperbolic system with relaxation. So it will behave like compressible Navier-Stokes with heat conduction, but all wave speeds are finite, right from the start. Now we do again check of asymptotic preserving property. So we basically solve the full system and compare with the exact solution of a smooth problem for the compressible Euler equations. And so, I mean, it's not really exactly invisible. I mean, we have to choose some parameters, say small relaxation times, but not to 0. I mean, we cannot do really 0. We choose small relaxation times and check with the exact solution of compressible Euler, and we get, say, reasonable results. Yeah, so now let's do, say, some classical test problems of fluid mechanics. Yeah, and classical stuff, yeah, laminar glass boundary layer flow. Sorry for the fact that you can't see the exact solution, but the reference solution, but it's very, very similar. Hagen-Poiseuille flow as in a duct. Okay, the parabolic velocity profile is recovered. Remember here there is no Laplace operator in this PDE. It's first-order hyperbolic PDE system with stiff relaxation, lid-driven cavity. Okay, you don't know this problem from incompressible Navier-Stokes. Okay, so you solve. This is the strain tensor A, just to give you an idea how this quantity looks like. Actually, it seems that it's quite nice for flow visualization, yeah? Because you see all these structures emerging. Double shear layer, this is a Peshkov-Romensky model, and let's say an incompressible Navier-Stokes reference simulation. Yeah? So they match at least in the I norm, and that's again the deformation gradient, yeah? The A, the distortion tensor. Say from Karman vortex street, I mean, this is colorful fluid dynamics, compressible mixing layer. So that's a compressible Navier-Stokes reference calculation, and that's a calculation done with the Peshkov-Romensky model, showing here vorticity in these images, and there the deformation gradient A. 3D Taylor green vortex, just to give some additional results. Yeah. So now here I must admit we don't fit perfectly the DNS reference data, but it's reasonable, at least to the moment. We need to do it on perhaps finer grids. This would be all the 9 components of the deformation gradient tensor A of the distortion tensor at the final time. But just to see that you see this development of small structures, which you would expect. I said we can do viscous heat conducting fluids. Well, there is an exact solution of the compressible Navier-Stokes equations for Prandtl number 3/4 for a viscous traveling wave, for a viscous shock. Okay, so there's the Navier-Stokes reference solution against the Peshkov-Romensky model, and they fit perfectly well. Here you have heat conduction and viscosity both present. Yeah, so here's the stress tensor and the heat flux vector, yeah, with both models, with Navier-Stokes and the Peshkov-Romensky model. And now this is something you couldn't do with Navier-Stokes. Yeah? Now we set tau to infinity, say 10 to the power of 20. This model reduces to elasticity model. Yeah? Automatically, yeah? Just change tau. It's the only thing we need to change. So that is basically the result obtained with the Peshkov-Romensky model. For a so-called Lamb's problem, where you have a solid, elastic solid, you hit the surface with a point force, and then you get basically propagation of pressure waves and shear waves, and so-called Rayleigh waves on the surface. This guy also has a name, but I don't remember anymore. And so this is the calculation done with the Peshkov-Romensky model. This is just a reference calculation solving right from the start linear elasticity equations. So the results match nicely. So at that point, I can already come to the conclusion. But we have, first of all, a unified formulation of DG and finite volume schemes called the PNTL framework. We can use this one-step ADER approach in a very nice way, I think, for time-accurate local time stepping in the context of AMR methods, space-time adaptive grids. You don't need to interpolate, you just have all the data available at any intermediate time level you want, yeah, due to this QH predictor. And with this machinery now, we can solve hyperbolic conservation laws with non-conservative products and stiff source terms. I mean, here you have the stiff relaxation source terms on the right-hand side, which allows to solve, to our knowledge, the first hyperbolic model of continuum mechanics that is able to cover both fluid and solid mechanics in one single unified PDE system. And this model includes viscous Newtonian flows with heat conduction, as well as elastic and even viscoplastic solids. Actually, the fluid in reality is treated as a viscoplastic solid at the end of the day in this model. And this is a formulation with finite wave speeds. So all the wave speeds are finite. You just have, say, longitudinal sound speed for the pressure waves and the shear sound speed. There's even a way how to compute this shear sound speed and the relaxation time from measurements. If you do ultrasound experiments, you can get both the relaxation time and the shear sound speed. So the model formulation is based on actually the main work of the late Godunov, which is not his Riemann-Circle, but the theory of thermodynamically compatible symmetric hyperbolic systems. It has been formulated in this way to cover fluid and solid mechanics for the first time by Peshkov-Romensky in 2014, and to my knowledge, these are the first numerical results for this. Well, all the wave speeds are finite, even in the Newtonian framework, and that cries basically to an extension to the relativistic framework, especially this year, because if we don't know, Einstein proposed the theory of general relativity exactly 100 years ago, 1915. Yeah, so since we already have seen some talks on relativistic hydro, yeah, now the question is, can we extend this model to include relativistic viscous and heat conducting fluids in the future, which would, by the way, automatically cover also relativistic solids. Yes? So, mentioning Einstein, well, wave speeds are finite, that is what is up to now believed, right? But that means the world is hyperbolic, so this is a very important workshop here. Yes? So, hyperbolic systems are important, yes, and we can reproduce all classical Navier-Stokes results with the hyperbolic model. But if Einstein said that wave speeds are finite and that therefore the world is hyperbolic, it means that 90% of the numerical analysts solve the wrong type of PDE. And with this joke, I can stop the presentation. And just one last publicity, if you are still interested in high-order methods, if your PhD students are interested in high-order methods, Tito and I organize, as every year at the beginning of February, a winter school on numerical methods for hyperbolic PDE. Thank you very much for your attention.
Thank you. Time for questions.
Yeah, so you're speaking about finite speeds of propagation, but when you compare with, I don't know, Dumbser or whatever, you try to extract infinite propagation speeds. How do they compare? What kind of regime?
Well, actually we have done, I haven't shown it here, but we have done actually a comparison. For example, if you solve, say, standard heat conduction equation, yes, with an explicit method, of course, I mean, the true wave propagation speed is infinite. If you use an explicit method, you have this parabolic time step restriction, which scales quadratically with the mesh spacing. If you solve diffusion equation directly, yes. If you solve the Peshkov-Romensky model, which is hyperbolic, with a finite wave speed, and the wave speed actually is bounded by the longitudinal pressure wave speed. Yeah? So the CS, the shear speed, is always inferior to the sound speed. That is the good news, yeah? Which also tells you something about the physics. Yeah? Shear waves can never propagate faster than longitudinal pressure waves, which also is somehow reasonable. Yeah? I mean, I cannot imagine if you look at heat conduction, yes. I mean, of course, parabolic heat conduction has infinite wave speeds, but it's a little bit difficult to believe that heat waves propagate faster than the longitudinal pressure wave speed in the solid, for example. Yes? And so actually what we get is that with the hyperbolic model, we get the same results as with the parabolic model, but with larger time steps. So that is good, I think. But it's the physics. I mean, it's not... Yeah, I mean, wave speeds are bounded by the longitudinal pressure wave speed, or in the worst case, by the speed of light. Okay, but say longitudinal pressure wave speed is upper bound. Then no wave speed is larger than that.
And can you get this from some kinetic formulation in which you...
Well, this is something that still needs to be explored. We have not done anything in that direction, but it would be interesting to check whether now this kind of model can be linked somehow to kinetic theory, right? Where also the origin of everything is hyperbolic, right from the start. And you don't assume anything about the stress tensor, right? I mean, you have the collision integral, and from there the things naturally follow. But we have no idea so far how to connect this stuff to kinetic theory. Unfortunately, but perhaps there is room to discuss with experts from kinetics.
More questions? Max?
Just have a remark. So one remark is that actually this is connected to the kind of approach we developed for parabolic equation based on hyperbolic relaxation. So when you do hyperbolic relaxation for a parabolic problem, and of course, you get the parabolic problem in the limit of the propagation speed. But then, at the numerical level, the techniques that we developed were all based on the fact that we use a finite propagation speed at the numerical level in the parabolic system by using some frozen characteristic speed and this kind of approximation. In your case, it's the model.
It's from the model, from the beginning. Because
it was a numerical model.
Yeah. Actually, that is what Peshkov and Romensky in their original paper actually stressed, that it is not built to artificially reproduce the parabolic limit, but you start from this energy potential, and the rest basically comes out of it automatically. And in particular, this choice of the shear sound speed, perhaps it was a little bit too fast actually, but here. So this guy, so alpha is basically a characteristic speed for heat wave propagation, and the CS is the shear wave speed, which for a solid, this is a known quantity. And you can compute it from the Lamé constants, which are usually known for most solids. Now for a fluid, it's not, people never bothered about measuring a shear sound speed, but the ultrasound people, they do actually bother, and at certain frequencies they find that a fluid behaves like a solid for ultrasound measurements. So now there are relations, I haven't put them here, but we have relations for the effective wave speed of a wave package in the limit tau to infinity and in the limit tau to 0. And if you can measure both with ultrasound, then at the end you can compute from that the shear sound speed in the fluid and the relaxation time tau that is actually associated with the final viscosity that you use. But as you said, this is right from the beginning embedded in the model by the choice of the energy potential.
if there are no more questions, then let us thank the speaker again.